This video is going to consider one main idea, and that is how can we apply integration to problem solving? When we studied derivatives, we noted that graphically, the derivative represented the slope of a tangent line to a curve at a particular point. And to me at least, this very naturally corresponded with the more broad idea of derivatives representing the instantaneous rate of change of whatever quantity a problem might have been about. With integration, graphically, we've been discussing the area underneath a curve in between two boundary points. And again, speaking just personally, for me, I find that to be less intuitive of a connection to see how that can be applied more broadly to various problem-solving contexts. However, I think that if we consider one very basic example that you've certainly seen before, we should be able to start generalizing and make some sense out of this. Now, I've got a pretty strong suspicion that you've encountered this equation before, whether in a physics course or certainly in earlier algebra courses. Now, every single one of these problems, whether it was explicitly stated in the question or not, they all relied upon one key assumption, and that was that this rate was kept constant. And I want to take a look at that with a quick graph. Now my y-axis is velocity, so a constant rate of change in this case is going to be a horizontal line. And now if I start moving at time 0 and I continue moving until whatever time this happens to be, if I want to find out the distance that I've covered in that amount of time, I just take the rate, my speed, multiplied by the amount of time that I was moving, and I would get the distance traveled, which in this case would be the area underneath this curve. And if we had two times that we wanted to look in between, well, then we could just find the time in between those two moments in time and then multiply that by the constant velocity. Now, I'm getting ahead of myself a little bit, I guess, because this idea of motion problems is really what the book is going to focus on in chapter 23. Those are the most common word problem application type for integration that you tend to see in AP and IB exams. So we're going to talk a lot about this later on, but this really does illustrate the connection between integration and what I would call accumulation or net change. Because that's what this problem is about, right? Where you could think of an object accumulating distance over time, or we're talking about the net change in its position or displacement. And since we already know about definite integrals, we're already equipped to handle problems where the velocity is not constant. As long as we have a function defining how the velocity changes over time, we have techniques to calculate the area under that curve, which means that we will be able to determine the net change in position for the object that is moving. So I know I come at this a little backwards, and generally speaking, we would prefer to understand a general principle first and then be able to apply that to specific cases. But again, just speaking for myself, when I was first learning this material, I found it much more natural to understand the specific case of velocity over time, and then that enabled me to accept the general principle that anytime we're talking about calculating an overall change in a quantity over a time interval, we're just performing definite integration. And that's the big idea for today. So that's really all that we need to know to start attacking some problems here. If we're given a function which represents the rate of change of some quantity, by integrating that function, we can calculate the net change in that quantity between 2 points in time. So in this first example, we have a fairly nasty looking function. We've got sines and cosines going on here. And we want to find the following quantities and explain what they represent. So obviously we're going to integrate this function e of t, which can be done without use of technology. Maybe a little bit of substitution here, but it shouldn't be too bad. From there, we can just compute the definite integral. If we were to do part A, we can substitute in 0 and 12 in for t into each of these, and that's not too bad, actually. It looks like it could be done without a calculator completely. However, we do have these coefficients here of 3.6 over pi and 0.6 over pi and 0.775t. So you're going to use a calculator for this particular problem in the end anyway, so really you're just going to skip over this entire step and just calculate the integral using technology, of course. So there isn't a lot of excitement to be seen in the numerical values. However, we do need to be mindful of what these numbers mean. So we read the problem really carefully. We see that T is the hours after midnight each day. So in part A, our integral from 0 to 12, this gives us the power consumed in the city between midnight and noon. So they call that the morning power. And then 12 and 24 is going to be in between noon and midnight. So they're going to call that the afternoon power. And then from 0 to 24 is the entire day. This second one is an example from the previous curriculum's version of our textbook, and it changes the situation ever so slightly. So marginal cost, we've spoken about that before. We have a function here which represents the rate of change in cost for producing one additional earn, in this case, is what we're making. Now, what's different about this problem is we don't have a definite integral with boundaries. I suppose a somewhat reasonable but very wrong first guess would be to go from 0 to 100, since they want the cost of producing 100 earns. But the problem with that is, remember that a definite integral is going to be defined on a continuous interval. So if we were to take an integral from 0 to 100, and we're counting earns, well, earns are only going to be produced in integer values, but a definite integral from 0 to 100 is going to be ranging across all of the infinite numerical values in between 0 and 100. So that really doesn't make a whole lot of sense. So instead, where I think we'd begin here, since we have a derivative function, let's just start off by integrating it. This is polynomial, so that's fairly easy. We're going to get a nice expression with a plus c at the end. So we might ask ourselves, what can we do with that plus c? Well, we're told that the initial costs before producing any earns are 185. In other words, our cost when we produce 0 earns is 185. That means that we can solve for c. c has to be 185. Oh, well, this is our function for producing x number of earns, so we're just going to put 100 into that, and we've got an answer. Here we have another example from the old book, a little more interesting, I think, so please take a moment, read through it, give it some thought, and when you're ready, we will continue. So again, we have an equation here with a derivative. By the way, this is called a differential equation, and we're going to study these in much more depth later on in the course. For now, we're just dealing with very simple ones, so your plan, at least for the moment, is if you see a differential equation, you're going to integrate, just like we did in the previous examples. So we integrate here, and this is a pretty easy integral to calculate. We're going to have an ln show up, and again, we need to figure out what the c is. A little bit harder than before. We can't just put in x equals 0, because x is only ranging from 2 to 4, and at one of those values, specifically 2, we know exactly what the temperature should be, because 2 is the radius of the inner circle, and everything inside that circle has a constant temperature of 100 degrees Celsius. So when x is 2, the temperature is 100, and that gets us a value for C. And then we can substitute in x equals 4 to work out what the temperature is of the outer surface of the tube. So I'm going to end there. Again, the main idea is you've got a function representing the rate of change of something. You're going to integrate that function, and that's going to get you the net change, or it'll tell you how much of the quantity you have accumulated from time A to time B, or in the distance from point A to point B, however you want to think about it. Other than that, there's really no tricks or secrets that you need to worry about. What I have on screen now is just some further applications of this topic into the realm of physics. Depending upon your background, you may have studied force to move objects. However, most likely you were dealing with constant forces. Well, guess what? You can extend this idea in the same way to deal with variable forces, and then you can do more and more complicated things as you see here. If you're interested in this, many calculus textbooks will have this in it, so you can go look it up, but it's not in the AP and it's not in the IB, so you don't need to worry about it, and I'm not going to bother with any more examples in this video. So until next time.